So next we will discuss collision density. Am I audible? Sometimes we wish to get rid of the dependence of reaction rate on the thickness D of the target. We may derive an expression. We may derive an expression for the dependence of flux on the neutron energy in terms of the moderating region, which can be derived from neutron balance in the slowing down process in infinitesimal element D in energy space, just like we define infinitesimal volume element earlier. Therefore, if phi E is the neutron flux of energy E for unit energy interval, the number of neutrons in unit meter to the power minus 3 second to the power minus 1, which are leaving the element D due to scattering collisions, can be represented as sigma S, which is a function of E, multiplied by phi, which is a function of E, dE, where sigma S is the macroscopic scattering cross section at energy capital. This quantity sigma S, which is a function of E, and phi, which is a function of E d, is called the collision density of neutron of energy E. So, angular neutron density. Just like number density, we define angular neutron density N dqr dqv as the number of neutrons in volume element dv about r with velocities in dqv about v r time t. However, instead of vector variable v, often it is more convenient to use the scalar variable e and two-dimensional vector omega, so that the variable v in Cartesian coordinate system, the components are vx, vy, and vz, and in a spherical polar coordinate system, v theta and phi change to e theta and phi. Polar coordinate system. And in the phase space, and dqv is nothing but v square dv d omega, where d omega is the solid angle which can be defined by sine theta d theta d phi. So instead of the number density in dq r dqv, we choose to work with n dqr d d omega, which represents the number of neutrons in volume element dqr about r with energies between E and E plus D moving within a solid angle d omega about omega in time t. For an assembly of neutrons, we consider average quantities so as to make up for the fluctuation in the system if any. Proceeding further, let us consider a volume element dv at a position r as shown in the figure. Here you have the Cartesian coordinate system where the components are x, y, and z. So the angular neutron density n can be defined such that at any instance of time t, n, which is a function of r e omega t dv, d omega d gives the average number of neutrons in the volume element dv at r moving within a solid angle d omega about omega as depicted in the figure, and having energies between E and E plus D. Okay. Then we'll discuss neutron density. By integrating the angular neutron density N over angular directions, we get neutron density N R E T. So your N is equal to integration 4 pi N R omega E T d omega. at time t, n dV d gives the average number of neutrons in the volume element dV at R having energies in the range E and E plus T. Okay. Am I audible? Am I audible?
Yes, sir.
Am I audible?
Yes, sir, you
Classroom, are you listening me?
are audible to us.
Am I audible? Please just text a message whether I am audible or not. Am I audible? Am I audible? No response, whether you are in the classroom or not. Am I audible? Audible?
Yes, sir, I can hear you.
Am I audible?
Sir, whom are you asking?
Nobody is responding.
Yes, sir, repeat.
Classroom, Bhubaneswar. Are you listening me?
Okay, sir.
Am I audible? Am I audible? Anybody in the class? Am I audible?
Yes, sir, I am present and I can hear you perfectly.
Okay. Am I audible now? Is the screen visible?
No, sir.
Okay. Is the screen visible?
Yes, sir. Yes, sir. Yes.
And in electric and magnetic system, the flux is a vector quantity. In a reactor physicist's point of view, neutron flux is a scalar quantity. Okay. Electron flux having electric field and magnetic field are vector quantities. But neutron flux is a scalar quantity. So when we define the angular neutron flux phi, which is a function of r, omega, e, and t, it can be represented as a product of velocity or speed and angular neutron density. Speed and angular neutron density n. So phi can be written as v multiplied by n, where both phi and n are the functions of r, omega, e, and t. So when you have phi is a function of r, omega, e, and t, you can write it as an integration of 4 pi phi d omega. Okay. Then your angular current density. Surface area A is of utmost interest. Your surface area A is a vector quantity directed along the perpendicular directed normally to the surface. A cap is directed normally to the surface. So surface area A is a vector quantity. And n cap is nothing but the unit vector normal to the surface. So n cap can be written as A vector divided by magnitude of A vector within a solid angle d omega about omega vector. Then angular current density is defined as the number of neutrons crossing the surface of area dA at the space point r in unit time and having energies between E and E plus a D. So mathematically we can write J is equal to V multiplied by N. Okay. So this can be written as omega multiplied by phi, where phi is a function of r, omega, E, and T. This is also known as angular current. Okay. So angular current is a vector quantity. Your normally current is a scalar quantity. I is a scalar quantity. But angular current of that of neutron is a vector quantity. The neutron current density. Neutron transport we express streaming in a certain direction in terms of neutron. So we can define current density as the number of neutrons having energies lying in unit energy interval around E, crossing the surface area dA at space point r per unit time. So mathematically we can write it as V multiplied by N d omega cos theta. So this gives the number of neutrons in energy range d about E and solid angle d omega about omega crossing area dA in time delta. So we can integrate J dA over all angles to get the number of neutrons having energies lying in unit energy interval around E and crossing the surface area dA at space point r per unit. Therefore, integration for I J dA d omega is equal to n cap dA integration d multiplied by n d omega. So this can be written as dA n cap multiplied by J, where J is called neutron current density or neutron current. Okay. then total neutron density, total neutron flux, and total neutron current. From the above expression, total neutron density N is obtained by integrating the previous equation, which I have discussed earlier. That is, N is equal to integration 4 pi N d omega. This can be written as N is equal to integration 0 to infinite d integration 4 pi N d omega. If angular density is independent of omega, it is said to be isotropic. So N has directional dependence. It acquires particular significance near the boundary of a surface or a source of neutrons. So anisotropies in angular density near a boundary or a neutron source can be shown in the figure. I have showing in the slide. Similarly, total neutron flux phi is obtained by integrating flux density over energy, as shown here. So total current J can be expressed as J is equal to integration 0 to infinite d integration 4 pi J d omega. So both J and phi have units of centimeter inverse, second inverse, centimeter to the power minus 2 second inverse. The only difference being that J is a vector quantity and phi is a scalar. So vector quantity has component in any direction. That is why neutron current is the net rate at which neutrons cross a unit area of a given surface at space point r and a time t perpendicular to that direction. However, being a scalar quantity, I gives the total rate at which neutrons cross a unit area regardless of orientation. However, there is a more convenient quantity of describing neutron leakage or flow to the surface of reactor core, while phi is more suitable for characterizing neutron reaction. Neutron reaction rates in which the total number of neutron interactions is of interest. Then we'll discuss partial neutron. Are you getting it? So, partial current are required to be calculated so as to give the total rate at which neutrons cross a unit area from one side only. Say from left to right, J subscript plus along positive x, or from right to left, that is Z subscript minus. So you can write J plus minus vector is equal to integration 0 to infinite d multiplied by integration 2 pi plus minus d omega n vector n cap multiplied by J vector plus minus, which is a function of r omega e and t. There are 2 pi plus minus is used as a convenient notation to remind us that angular integration is performed only over direction with components along the surface normal, that is 2 pi plus, or in the opposite direction 2 pi minus. To understand this better, let us integrate it over 2 pi and the integration over angle to be performed for direction along 2 pi plus or opposite, that is 2 pi minus, to the outward drawn normal. For example, the polar coordinate specifying omega present along the normal to the surface. Then in J plus vector, integration polar angle phi would range from 0 to 2 pi, while theta would range only from 0 to pi by 2. This can be shown in the picture where dA is the distance. When J and dA is shown and n cap is perpendicular to the surface. Okay. So partial and total neutron currents are represented as shown in the picture. So net number of neutrons in dE above dE crossing dA from minus to plus during time del t is nothing but n cap integration omega phi d omega, which is nothing but n cap j d dA del t. So there are a few assumptions in derivation of neutron transport equation. What are those? Neutrons may be treated as classical point particles specified by their position and velocity. By so doing, The wave HR as well as the magnetic moment and spin of the neutrons are equal. Are you getting it? Are you getting it? The second assumption is the interaction of neutrons with nuclei takes place via nuclear force. This allows the motion of neutrons to be described in terms of their collision with the nuclei of the medium. So for simplicity, we can consider a neutron to move in a straight line. It is safe to ignore deviation from the average number of neutrons in a medium. By making this assumption, we ensure that angular neutron density can be treated as a continuous function rather than a random number. In a typical reactor with a high flux 20/16 and 20 to the power -2, second to the power -1, neutron density is nearly 10 to the power 11 n centimeter to the power -2. This number is significantly lower than the number density of medium nuclei, that is 10 to the power 22 nuclei centimeter to the power -2. It means that neutron-neutron collisions can be ignored. In a fusion process, neutrons are emitted isotopically. So, for all of these assumptions may not hold always. It will be discussed as situation arises. Okay. So there are some solutions and terminal questions. You may go through this. Then we shall discuss Boltzmann transport. So Louis Boltzmann is the greatest physicist of German origin, and his pioneering work the field of statistical physics is noted. Boltzmann has derived the transport equation for. Am I audible? बोल रहे हैं आप लोग? Okay. So, to derive transport equation, we first identify the processes involved in neutron transport in a medium. Basically, transport equation specifies conservation of neutrons, that is, balance of neutrons of given energy in range d above t and directions in d omega above omega in time interval del t in a volume element. Therefore, we can write number of neutrons in a volume element is nothing but gains minus losses. For the gains in multiplying system, we consider contribution due to future, external sources and scattering. On the other hand, neutron losses can be because of collisions and leakage due to finite size of the medium. In steady state, this balance equation can be written as minus omega factor L minus summation phi plus summation phi d plus s is equal to 0. There are three terms and there are four terms out of which one is your s. So del is the gradient of it. So your phi is nothing but a function of r, omega, and e, and angular flux of neutrons. Phi dash is equal to phi dash, where phi dash is a function of r, sigma dash, and e. It is angular neutron flux for neutrons of energy E dash moving in the direction omega. So your sigma is equal to sigma is a function of r and e. The total macroscopic cross section for all interactions of neutrons of energy capital E and position r vector. So your F dash is equal to F r omega E transition from E to omega, and E is the probability that the neutron at r with energy E dash and moving along omega dash will have energy E and direction omega after an index. easily by introducing an integrating factor of the form sigma on the both sides. So integral form of neutron transport equation is very much important. The number of neutron energy is moving in direction omega due to collisions and independent sources at r minus s star omega in the system and all earlier times t minus s double dash by v. This is represented by q. The attenuation factor exponential minus sigma s double dash is a measure of decay of neutron flux with distance due to absorption and scattering from the point of origin to the point of observation. The exponent is called optical path length or the optical thickness of the medium. This is denoted by alpha, which is a function of E. Are you getting it? So, for non-uniform media, neutron cross-section depends on R. In such cases, the attenuation factor takes the form exponential minus integration 0 to s double dash sigma ds dash, and the optical path length becomes alpha is equal to integration 0 to s double dash sigma ds dash. So, Parallels equation. This is an important equation, and this represents a simpler form of the steady state scattering and contribution of external sources can be taken to be isotropic. Then the integration over all directions simplifies sigma is equal to sigma by 4 pi and S0 is equal to S0 by 4 pi. Okay. So, this can be written as phi 0 is equal to integration d dv dash by 4 pi r square exponential minus sigma 0 r integration 0 to infinite sigma s0 phi 0 d dash plus s0 where r is equal to r vector minus r dash vector. This is Pare's equation. For an infinite slab of thickness 2a, Paul's equation can be written as phi 0 is equal to half integration minus 1 to plus 1, minus a to plus a, dx dash e1 integration 0 to infinite summation e dash to e phi 0 plus s0. Okay. So, in the next class, we shall discuss the rest part of this. Okay. The next part of the diffusion equation, where we can discuss we have derived diffusion, where we can derive diffusion equation starting from most general neutron transport equation, solve diffusion equation using initial boundary and source condition, and discuss validity of diffusion equation. So thank you for patiently attending this class.